Okay, this time I'm going to explain section 8.7 of the calculus, which is numerical integration. Okay, just take a look at the first paragraph here. So the antiderivatives of some functions like sine x squared, 1 over ln x, or square root of 1 plus x to the fourth have no elementary formulas. So that means we cannot find express the answer of this kind of integrations. Yeah, with symbols we have learned in the high school. So how should we do with this kind of problems? For the indefinite integral, we cannot really do anything, so that's done. But for definite integral, where you are going to find the area under the curve, there is some way to approximate the values. So let's say we have a function y is equal to fx and over the interval of a through b. There are two techniques explained in this section, which is trapezoidal rule and Simpson's rule. And the idea is you are going to find the area under the curve by splitting the interval into several intervals. And in each interval, you only pick the endpoints. And instead of finding the area under the curve, we are going to approximate this function by a much simpler function, a linear function. In this interval, a line that connects these 2 points, line connects these 2 points, and line connects these 2 points. And we are going to find the area under this orange curve or orange segments. So you will get some kind of area that is different from the area under the curve, but it should be close. This idea is called the trapezoidal rule. Okay. So let's going to derive the formula for the trapezoidal rule. First of all, let's say this is A and B. We are going to divide it into n congruent segments. And let's say each width of the interval is delta x. Delta x is basically length of between A through B divided by number of intervals. So let's divide it by n. So n intervals. Okay. So this delta x represents the length of the subintervals. Let's give the values have a sequence where the first A is equal to x naught, and the next stop point is x1, and next stop point is x2, and so on, and the last one is going to be xn. So that means x1 is equal to x1 plus delta x. x2 means x naught plus 2 times delta x, and so on. So xk represents x naught plus k times delta x. Okay, so that's what it means. We are going to find the y value at these points. So y value at this point means basically you just plug in these x values into the function fx. Okay. Now let's look at the first trapezoid here. How do you find the area of the trapezoid here? So the trapezoid can be found by upper base plus lower base multiplied by height, then divided by 2. So the height here is y value at x is equal to x naught. y value here, this height here is y value at x is equal to x1. So this length can be expressed as f of x naught. And this one is f of x1. The height here is delta x. So the first trapezoid has an area of upper base plus lower base times height, delta x, divided by 2. So that is equal to this. If you do the same thing for the second trapezoid, it's going to be base almost identical, same height divided by 2, but now the upper base is f of x plus 1, and the lower base is f of x2. Likewise, when you look at the third trapezoid, it's everything basically same, but the upper base going to be f of x2, and the right one going to be f of x3. So if you repeat this one for n trapezoid, the last one will be f of xn minus 1 plus f of xn. Adding those together, factor out delta x over 2. The total area of the trapezoid, sum of the trapezoid will be 1 of this plus 2 of this plus 2 of this plus 2 of this, 2 of that, 2 of that, 2 of that, and 2 of f of xn minus 1 plus just 1 of the last one, f of xn. Okay, this will give us the area under the trapezoid. I mean, under the segments. Okay. So here's the idea of the trapezoidal rule. So that's going to approximate a short stretch of the curve with line segments. To approximate the integral of f from a to b, we just add the area of the trapezoid made by joining the end point of the segment to the x-axis. Now here it said y1, y2, y3. It is same thing as this. So in the textbook, it said this is y0, this is y1, and this is y2, and so on. So here's a formula for the trapezoidal rule. So delta x over 2 times 1 of y1 plus 2 of y1, y2, y3 up to yn minus 1 plus just 1 of yn. まあ、台形がこう並んでるだけでして、まあ、そのね、台形の面積をこう足していくんですけど、まあ、乗定足す過程をこういうふうにやるじゃないですか。で、その次もね、その次のところでも、あらら、消えちゃったよ。ストップ。OK。まあ、こう台形のね、これ乗定足す過程っていうのをやるんだけど、で次のところでも乗定足す過程をやるじゃないですか。ね、次のところでも乗定足す過程とかってやるんで、ここの数字2回使われてんだよね。で、その次の時も、まあ、乗定足す過程ってやってるんで、ここの数字も2回足されてることになるわけだ。で、まあ、一番最後のとこだけは、まあ、乗定足す過程で終わるんで、ここのね、両端だけは1回しか使われないんですよ。でもそれ以外の高さは2回ずつ使われているので、まあ真ん中はね、2× になります。Okay, so let's apply the trapezoidal rule to the simple example, simple function. So let's do example 1. Use the trapezoidal rule with 4 subintervals to estimate the integral of 1 through 2 of x squared dx. with n is equal to 4. So the curve itself really doesn't matter. We just draw the picture. And here is 1, and here is 2. Split into 4 subintervals of the equal length. Okay. And we are going to make a trapezoid, 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 trapezoid. Okay. But we don't need to know the picture is. So what we really need to know is xi, I starting from 0, 1, 2, 3, 4. So the smallest x value is 1, largest x value is 2. Each interval is 2 minus 1 divided by 4 because the number of the subinterval is specified at 4. So the subinterval length is 1/4. So here it's going to be arithmetic sequence whose increment is 1/4. So this is going to be 5/4. This is going to be 6/4, which is same thing as 3/2. The next one is going to be 7/4, and next one is 2. This is arithmetic sequence. Now, we want to know what is the y value at this point. So y value, the function we are using is x squared. So this is going to be just 1 square. This is 5/4 square. This is 3/2 square. This is 7/4 square. And this is going to be equal to 2 square. We are going to use these values as we are using this one, okay? So the area, total area is equal to delta x over 2 of first value plus 2 times the second y value, third one, fourth one, and last one is only used once, okay? So it's going to be 1/4 over 2 times first y value is equal to 1. Second one is multiplied by 2. Multiplied by 2. Third one is multiplied by 2. Fourth one is multiplied by 2. And last one, you just use it. Okay. It's not a simple value, but it's going to be 1/8 times 5 plus 9/2 plus it's going to be 74/8. 74/8, which is 37/4. So it is 455, 475. So it's going to be 32 and 75. So that's going to be our approximation. So this is the estimate we obtained using a trapezoidal rule. And of course, that's going to be different from the actual value. Let's find actual value to compare the result. So if you know the definite integral, it's going to be 1/3 x cubed. And you plug in 1 through 2. So it's going to be plug in 2, you want to get 8/3. Plug in 1, you want to get 1/3. So the actual value is 7/3. This is actual. This is the estimation. Okay, so how close are they? 7/3 is same thing as 2.33333. 75/32 is same thing as 2 and 11/32. Well, this is very close to 333, 1/3, but I don't know exactly, so I have to do it. 396, 4, 128, 396, 7, and so on. So it's going to be 2.3437. So you see, it's kind of very close in this case. Okay, so that's something like this. So you just make a table and you just plug in into this formula. Okay, so it's easy to do it if you have like a spreadsheet work or some calculator. This is much easier to do. Okay, now let's move on to the next one, which is about the Simpson's rule. The idea is very similar to trapezoidal rule. For the trapezoid rule, your estimation is based on the simplest function, a line. So line can be determined when you have two distinct points. Then you can draw a unique line connecting those 2 points. So that's the idea of using the lines to estimate. In Simpson's rule, idea is you are going to estimate it using a parabola. To uniquely determine the parabola, you need 3 distinct points. When you have a 3 distinct points, there is a single unique parabola that goes through these 3 points. So I don't know how to draw it well, but something maybe like this. Okay, so there's one parabola that goes through 3 points. Remember, line is ax plus b, so you need two informations. Parabola is ax squared plus bx plus 3c, so you will need 3 different informations to determine ABC. So Simpson's rule is approximation using quadratic second degree polynomial instead of first degree linear function. That's our idea is that's the difference, and everything else is the same. So how do we find the parabola? So that's kind of hard to do, but you basically use those 3 points to find the parabola that goes through those 3 points. So how do we find it? Well, look at this example. Yeah, forget about the x values. So this is just taking example. Let's pick the center of x value is 0, and the left one is negative h, and the right one is positive h. And let's say y value here is y0, and y value here is y1, and y value here is y2. So basically, this is minus h comma h y0. This point is 0 comma y1, and this point is h comma y2. How do we find the parabola that goes through those 3 points? Let's find it. So let's say the function is a parabola. So y is equal to ax squared plus bx plus c. And this is, you have a negative h comma y0 is passing through this point. I mean, this function. So it's going to be y0 is equal to h squared a minus hb plus c. Also, this goes through h comma y2. So y2 is equal to h squared a plus hb plus c. And another one, 0 comma y1. So it's going to be y1 is equal to c. We need to solve this system of equations for ABC. Now, c is obviously equal to y1, so that's done. So now next thing to do is find a and b. So here, let's add one, well, let's subtract one from another. So it's going to be y2 minus y1 is equal to 2h over times b. So we can find the equation is equal to b is equal to 2h y2 minus y0. And a, you can find it by adding together So y0 plus y2 is equal to 2h square a plus 2c. So 2c is same thing as 2y1. So it's going to be minus 2y1 over 2h squared is equal to a. So the parabola that goes through those 3 points can be expressed as using this one. Y is equal to y2 plus y0 minus 2y1 over 2h squared x squared plus y2 minus y0 over 2h x plus y1. Okay, so that's a parabola. That's a parabola. Now we are not really interested in finding a parabola, but we were interested in finding the area under the parabola. Okay, area under the parabola. So we are going to integrate this one for negative h through h to find area under the curve. Okay, because that's what we are going to use for approximations. So this is just a constant number. It's independent of x, so it doesn't change at all. So it's going to be, just leave it as it is. And when you integrate this one, it's going to be 1/3 h squared h cubed times 2. And when you integrate this one, it's going to be disappeared because this is an odd function. This is an odd function. So when you integrate from negative h to h, it disappears. And when you integrate this one, you want to get 2h times y1. Okay, so simplify this expression. It's going to be 3rd y2 plus y0 minus 2y1 times h plus 2h y1. So that's the area here. H is basically delta x here. So let's put h out. And I hate 3 here. Let's put 3 out as well. So when you factor out these two, it's going to be y2 plus y0 minus 2y1 plus 6y1. Is that correct? So it's going to become h over 3 y0 plus 4y1 plus y2. Getting simple, right? So that's the area under the parabola in these two subintervals. Once you understand this one, we can understand the Simpson's rule. So let's say this is the first point, A, and this is last point, B, and this is x1, y, x2, and so on. So we use those 3 points to find the area under the curve using the parabola, and that's going to become this. If you use the same thing for x1, x2, x3, then you want to use those 3 points, and the result should be, instead of y1, y0, y1, y2, you want to get, well, sorry, not x2. I should use x4. So this one is for here. Now for the next 2 subintervals, you should have the area of h over 3. And instead of 0, 1, 2, you should have y2 plus 4y3 plus y4, because you just started with different values. So approximating here gonna be something like this. And you do the same thing for the next intervals. For example, x4, x5, x6, you have again 3 intervals, 3 points, and you can draw a parabola like this. And this area should be h over 3 of first one times 1 the second one times 4, and third one times 1. And so on. So if we repeat this way, you see this y2 is added twice, y4 is added twice, and so on. So it's kind of end up with something like this. So let's say h is delta x. So the total area is going to be delta x over 3 times first y value plus 4 times the second y value plus only one of them here, but you are going to add another one here, right? With y2 here, and you have another y2 plus 4y3 plus y4. And next one is 4y4 plus 4y5 plus y6, and so on. So you see it's going to be 2 of them, 4, 2 of them, 4, 2 of them, and so on. So if you just look at the coefficient, it's going to be like 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4. And the last one is going to be just 1. Well, my handwriting is not good, so just look at the next page here. Okay, so here's the Simpson rule, and you just use this formula to find the approximation. So you see delta x over 3, 1 of y0, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, and last one is going to be 1. Okay. Now, this requires the number of the interval should be even, because you see 2 intervals is used at the one time. Okay. Now, let's look at the example 2, how we do the computation by hand. We don't want to do it by hand, but let's do it by hand to understand what's going on. So it's going to be integral of 0 through 2 of 5x to the fourth dx. And let's use the interval is equal to 4. Okay. What is delta x? B minus a over n is equal to 2 minus 0 divided by 4. So the interval, each interval has a length of 1/2. Okay, so 0 through 2 split into 4 pieces. So first number is 0, and the last number is 2. And you each go by 1/2. Increase 1/2, increase 1/2, increase 1/2, and increase 1/2. So those are the key points we are going to use. Okay. What are the y values at these points? What are the y values at these points? Well, y value in this case is 5 times xi to the power 4th. So the first one is going to be 0. This is going to be 5 over 16. Yeah, to the power 4th. It's going to be 5. This is going to be, well, 3 over 2 to the power 4 is going to be 81 over 16. You multiply it by 5, so it is 405 over 16. And the last one is 16 times 5, it's going to be 80. So now we have sufficient number of informations. Now let's use the Simpson's rule. So by Simpson, the area under the curve is approximated by delta x over 3 of first y value plus 4 times the second y value plus 2 times third y value plus 4, and last one is going to be just one of them. Okay. So using this one, it's going to be 1/2 over 3 times 0 plus 4 times 5 over 16. So it's going to be this, and 2 times 5. And this times 4, which is going to be 5 over 4 plus 1 times this 80. So it's going to be 1 over 6 times 90 plus 410 over 4, which is 102.5. So 192.5 divided by 6, which is, let's make it 2 decimals. So So 32.083. 32.083. Well, that's our approximation. Let's integrate to find the exact value to check how close it is. So after integrated, it's going to be x to the fifth. That's equal to 32 just. So this is quite close, the very close number. Yeah, it's quite nice. The only, yeah, if you take a ratio of these two, it's almost like 100% correct. Yeah, like 90 something. Yeah. So now look at answer here. This estimate differ from the exact value by only 1/12. Yeah. So it said 0.3%, 0.3% ですね。That's quite good with just 4 subintervals. Okay, next one, I'm not going to do derivations here, but just say about the upper limit for the errors. So whenever we use approximation technique, the issue arises as to how accurate the approximation might be. Yeah. So when we do the approximations, we want to know how accurate it is or how bad the error could be. So the following theorems gives the formula for estimating the errors when using these rules. Okay, the error in here means the difference between the approximations and the actual value. So in this case, the error is the absolute error gonna be just the difference between the exact value minus approximate value. Okay, so in this case, it's going to be minus 0.83. Now, here's the theorem. Let's read the theorem. So if the second derivative of f, is continuous, and m is any upper bound for the value of the absolute value of f dash dash on the interval, then error can be at most this value. And for the error for the Simpson is at most this value. Okay, so let's do the error analysis for this one. So we used a Simpson rule right now. So let's use this maximum error possible for the Simpson rule. So first of all, the function fx is 5 times x to the fourth. We need the fourth order derivative. So f dash is equal to 20x cubed, f dash dash is equal to 60x squared, f dash 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 is equal to 120x, and f dash 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 dash, or f to the fourth derivative is 120. Okay, which is a continuous function. Okay, and the upper bound for this one is always 120. So this is upper bound we can use. So that is equal to m. So the error, absolute value of the error by the Simpson rule is at most 120 times. In this case, we use b is equal to 2, a equal to 0 for the interval. So it's going to be 2 to the power 5 divided by 180 times n to the power 4th, which is quite good. In this case, the interval we used is 4. So 4 to the power 4th. So that's going to be 180 times 2 to the power 8, 2 to the power 5, 120. So it's going to be 2/3 times 1/8, which is 1/12. So the maximum error we could have is 1/12. And in this case, we just got the maximum error because, yeah, this was negative 1/12. So maximum error possible is 1/12. So in this case, we got the worst possible case, but that means the estimation could be quite accurate because error is at most only 0.083 in this problem. Now let's use, what if we use the trapezoid rule? what if we use trapezoid rule? Trapezoid rule, we just use the same thing, but instead of fourth degree derivative, we just use this one. So f dash dash of x is at most 60 times 2 square in this case. So m is equal to 240. So error by the trapezoidal rule is going to be 240 times 2 cube over 12 times number of interval was 4, so it's going to be 4 square. So this is going to be 20 times 2 cube over 2 to the power of 4, and so it's going to be 10. 10. So that doesn't sound good. Yeah, so the error could be as big as equal to 10. Now, let's solve this question by trapezoidal rule because we already did some computation here. So let's check how bad the trapezoidal rule can be for this one. So using the trapezoidal rule, the area is going to be the delta x over 2 times first number plus 2 times the second one, 2 times third one, 2 times fourth one, and 1 times the fifth one. So using this, it's going to be 1/2 over 2, 0 plus 5 over 8, plus 10, plus 4, 5 over 8, plus 80. That's going to be 1/4 times 90 plus 410 over 8, which is 1/4, 90 plus 51.25. So that's going to be 141.25 over 4, which is equal to 35.31 something, 35.31 something. So not too bad. The actual value is 32, so not too bad, but you see the error is the error caused by trapezoidal rule is equal to 3.31, and which doesn't violate with the result we had because error is at most 10, at most 10. And in this case, the error we got is 3.31. Okay. So that's how we use this error formulas. Okay, so the example 3 shows how do we find the maximum possible area for if we use the Simpson rule. And that's, we already did it. I already explained it. And the next one is example 4 is estimate the number of the intervals we needed to make the error smaller. So we want to make for example, if we want to make error to be less than 0.00001, how many intervals we will need? So in that case, because the possible error, maximum possible error is this, we want that to be less than 10 to the power of -4. And we want to find n that satisfies this. In that example, we found out m is 120, and this one was 2. So we just do like this. So it's going to be 2 over 3 times 32 times 10 to the 4th and to the 4th. So that's going to be quite big number. Is that correct? So n must satisfy this. So how big is this? Well, approximately 210,000. So n should be greater than 4th root of 210,000. We want that integer, and n must be even. Well, I rewrite this one as 10 to the power of 4 times 1, 2, 3, 4 times 21. So it's gonna be like 10 times 4th root of 21. So this is something like 2 point something. So it's gonna be like n must be greater than 20 something, 20 something. I don't know, maybe 21 or 22 or 23, I don't know, but n must be greater than that. So I need a calculator to find a better number, but basically the number of intervals we need is because it's using Simpson rule, it must be even and must be greater than this. So probably 24 maybe, or 22. It depends on the value here. So I need a calculator. Yeah. Yeah, so okay, so I was wrong. So according to the calculator, this is 21.5. So we will need 22 sub-intervals. Okay, so that's complete explanation for this section. Thank you for your participation.